Hello everyone, can you hear me? Am I audible to everyone?
Yes, sir.
And this screen is also visible, which I have shared.
Yes, sir.
Okay, thank you so much. Yeah. So we will take 1 or 2 minutes further. Let the others to join, and then we will start. Okay. So let us have a quick recap of what we have done in the last class. So in the last class, we started looking at heat transfer through variables surface area. So again, we have argued. Hello, yeah. Hello. Is there any question? Hello.
No, sir. Just the screen is lagging a bit in between, so like it's not being continuous.
So screen is not visible.
So it is visible, but it is lagging. Maybe some issue with the network.
Okay. Just stop me in between if something is not going well. Okay.
Okay, sir.
Okay. So what we have seen in the last class is the heat transfer when there is a variable area is present. And again, we have argued extensively that whenever we have a planar geometry, like a flat surfaces like layers, if we are having the layers, in that case the area is constant, the heat transfer area is constant, there is no generation term, there is no accumulation term, and therefore we don't require a shell balance at all. Okay. But when we are looking at the heat transfer through a cylindrical surfaces or the spherical surfaces as shown here, if the heat transfer is taking place from outside to inside the cylinder or from inside to outside the cylinder through this radial direction, the area varies as we move from one location to the another along the radial direction, and in such cases we need to make a shell balance. Okay. Another thing which we have seen is whenever there is a generation term or accumulation term, again we have to make the shell balance. Okay. So we have derived the expression for both spherical geometry as well as the cylindrical geometry, how the rate of heat transfer is going to vary with respect to the radius, with respect to the temperature gradient, temperature difference that we have already derived, isn't it? Also, we have derived the expression for the composite sphere or composite cylinder. So composite cylinder, the equation is this. And just wait. Another important conclusion we had in the last class is the heat transfer through the cylindrical surfaces will be similar to the heat transfer to the flat slab. The only difference here is going to be the area which is calculated in this case should be with respect to the log mean radius of the cylinder. Okay, that is the only difference you are going to have. Other than that, the expression is going to be same. So here you can see 2 pi rm l, that is going to be the area, and this area is calculated based on the rm, where rm is nothing but the log mean radius of the cylinder. So if we put this 2 pi rm l as a area A, then this equation becomes AK delta T divided by the thickness, isn't it? So R naught minus Ri is a thickness, isn't it? So this is a same expression as what we have seen for a flat slab. Okay, a similar conclusion we can draw when we are looking at the steady state conduction through a sphere. Here also, if you look at the final expression for the rate of heat transfer Q, so rate of heat transfer Q here obtained as 4 pi Ri R naught K Ti minus T naught divided by R naught minus Ri. So here you can see 4 pi Ri R naught. This is nothing but a area of a sphere. Again, this area is calculated based on the geometrical radius of the sphere. So Ri R naught is nothing but the square of R, where R is nothing but the geometrical radius. So if we consider this as a geometrical area 4 pi Ri R naught, then this expression becomes area into K into delta T divided by thickness. So this also becomes the same as the expression what we have seen for a flat slab. The difference here is the area is calculated based on the geometrical radius, geometric mean radius. Okay. Again, unlike a flat slab where the temperature profiles, if I go back and show you, here you can see the temperature profiles are linear within a slab, isn't it? The slope of each of these profiles changes when we are moving from one slab to another. That is because the thermal conductivity is changing, isn't it? So other than that, when thermal conductivity is constant, when there is no accumulation term, when there is no generation term, when the surface area, heat transfer area is constant, you can see the temperature profile is linear here. But when we go back and see the temperature profile for the cylindrical case, here you can see this is the temperature distribution for the cylindrical case. This is not linear, this is non-linear. Okay. So this one has to remember. Similarly, if I go and check for the spherical geometry, here also you can see the temperature distribution is not linear. Okay. Again, one more thing you all have to note down here is even in case of a flat slab, if you assume that the thermal conductivity is a function of temperature, you will not get a linear temperature profile. You will get a non-linear temperature profile. So these are the things which you have to remember. You get only the linear profile when the thermal conductivity is not changing, when the surface area is not varying, when there is no generation term, when there is no accumulation term. In that case, in a flat slab geometry, you will get a linear temperature profile. Other than that, you will have to make a shell balance, and also you will have a non-linear temperature distribution, non-linear temperature profile. Okay, so let us start with today's class. So again, in the last class, we have seen one more case of a flat slab when there is a generation term is there. So slowly we are adding the complications in the analysis which we have done in the earlier classes. So this is one more additional complication added here, isn't it? A heat generation source heat source is added in the analysis. Again, this type of cases are commonly seen in chemical engineering or in process engineering. One of the notable example is a nuclear fuel element. If you look at the nuclear fuel element, there is a bombardment of the neutron is taking place, and because of that, nuclear fission takes place, which generates the heat energy. Okay, and this heat energy then is dissipated through the element. Okay. The another commonly seen example is a electrical conductor. You can take a electric wire. So because of the resistance, when the current is flowing through a wire, there is a heat generation takes place, and this heat is dissipated in a radial direction. Okay. One more example is a catalyst pellet, a spherical catalyst pellet. Here you can see because of chemical reaction, the heat is generated inside the catalyst pellet. Okay. So these are the commonly seen example when there is a heat generation is taking place inside the system. Okay. So in the last class, we have seen a simple example of a flat slab. This is the same example of a flat slab which we have seen earlier, but the only difference here is now we are also saying that there is a heat generation source is there, isn't it? Again, for a time being, what we assume that the thermal conductivity is not constant and is a function of temperature, and also the heat generation, volumetric rate of heat generation psi is also a function of x, is also a function of x. Again, what we are assuming here is the temperature on the left hand side of the slab is T1, temperature on the right hand side of the slab is T2. The cross sectional area is A, and the length of the slab is L. So with this, uh, the heat balance we have solved already, we have seen in the last class. So I will not go in a detail of this. So if we make a heat balance here, what we get is minus dqx by dx plus psi x equals to 0. So this is a generalized expression. This is a generalized expression. In this, we can put the Fourier's law of heat conduction, which is nothing but kT. Qx is given as minus kT dt by dx. If I put it, equation 2 is the most generalized expression. Okay. So in order to solve this equation, we have made some assumptions. The assumptions are the thermal conductivity kT we are assuming constant and is not a function of temperature, and a constant value k is used. So kT is same as k. The slides are visible to everyone. Hello. Some background knowledge
So
is.
again, the slides are visible, but they're lagging in between. So like when you're transitioning from one slide to another, so it's
So
showing a black
I am
flash.
now on slide number 24. The slide number 24 is visible.
Yes, sir, it is.
Okay, and also this pointer is visible, which I am moving from one place to another.
Yes, sir, it
So could you
is.
please show that
Sir, it is
once?
visible. I think it's Ashutosh's internet issue.
It is probably the internet issue. So can we go ahead? Hello, can we
Yes,
go
sir.
ahead?
Yes,
Yes,
sir.
sir. Yes, sir. Sure.
Okay, so the most generalized expression is expression number 2. So I will basically call this expression with their equation numbers so that you can, relate things. Okay. So the most generalized expression is expression number 2. So here you can see k is function of temperature, as well as psi is also a function of x, isn't it? Where x is nothing but the distance from the left hand side, isn't it? Correct. So in order to solve this expression, let us make some simple assumptions here. So let us assume that kT, which is nothing but the thermal conductivity, which is right now is a function of temperature. We can take a constant value k, which is independent of the temperature. So kT is same as k. The another assumption is psi x. We are assuming psi x is same as psi v, where psi v is nothing but the volumetric rate of heat generation, and which is uniform throughout the slab. It is not varying with respect to the x. Okay. So with these two assumptions, now we can simplify equation number 2. So with these two assumptions, the simplified expression becomes equation number 3, where uh, we can take this k outside of this bracket from equation number 2, and psi we can take on the right hand side, and if we rearrange it, what we are going to get is d square t by dx square equals to minus psi v by k, where psi v is a volumetric rate of heat generation which is uniform throughout the slab and is not varying with respect to x. It is constant. Similarly, k is also a constant. Thermal conductivity k is constant. So there are two boundary conditions. The boundary conditions are when x equals to 0, So we are looking at the left hand side of the slab. So then the temperature T is T1. Similarly, when x equals to L, T is T2. So if we put this boundary condition and in this equation number 3, we can find out C1 and C2, and C1 and C2 we have already obtained in the last class. The C1 and C2 are put into this generalized expression 3, and what we get is the temperature distribution, which is equation number 4. So unlike the equation, temperature distribution equation, which we have seen for a flat slab earlier without heat generation, this expression is a non-linear expression. Equation number 4 is non-linear. It is not linear. It is not linear. Temperature profile is not going to be a straight line here, isn't it? Again, we can find out how the heat flux is going to vary. So heat flux, this is the expression equation, the last equation. We can integrate this. So from integration, what we get is Qx is psi Vx plus C naught, where C naught is a different constant. C naught is not C1. So if we compare this equation with the earlier equation, if we compare, then you can see that C naught is going to be minus Kc1. C naught is going to be minus Kc1. So C1 we have already obtained. So we can put C1 here. We can find out how the heat flux is going to vary with respect to the distance from the left hand side x, and also how it is going to vary with respect to the overall temperature difference or the generation term that is given by this last equation. So Qx is given as psi Vx minus K in the bracket T2 minus T1 by L plus psi V by 2KL. Okay, this is the final expression. Again, one more thing I wanted to say is that this equation is not correct in the book. Okay, so whatever the expression I have given you here is correct. So let's move to slightly more complicated case, isn't it? So this is the simplest case of a flat slab, okay, with heat generation. Now let's move to a slightly more complicated case where we are looking at a cylindrical, system, cylindrical wire in which there is a heat generation is taking place. So consider a electric wire. Consider a electric wire carrying a current. The wire is of radius Ri, and over this electric wire, which is made up of some metal, over that there is a electric insulation is applied. So the radius of the insulation is R0. Okay. Again, as the current is flowing through this metal wire, the heat is generated, and this heat is dissipated outside. So outside temperature is T0, inside temperature distributed. So within this metal wire we can take the temperature as Tm, and within this insulation which is there outside this metal wire, we can consider the temperature in this as Tc. Again, Km and Kc are the thermal conductivity of the metal wire, and Kc is the thermal conductivity of the insulation applied over the wire. The volumetric rate of heat generation is psi V, and we are assuming that it is constant throughout the medium. So this is the geometry here. You can see the L is the length of the wire. R is the again here you can see the area of heat transfer. Since the heat is dissipated in a radial direction, my heat transfer area is varying as I am moving from the center to the outside, and therefore we need to make a shell balance. So in order to do that, consider a shell of thickness delta R at a radius R from the center. Okay, so here this is the shell which is shown by a dashed line here in between. The thickness of this shell or the thickness of this cylindrical element is delta R, and it is at the distance R from the center. Again, Ri is the radius of the metal wire, whereas R0 is the radius of the outside radius, which is also included the insulation. Okay, T0 is a outside temperature. So now okay, so as we were discussing, in this case, not only the heat transfer area is varying along the radial direction, but also there is a heat generation term. There is also a heat generation term. So clearly we need to make a shell balance. So let's look at the heat balance across the shell. Okay. So I am now on the slide number 27. I have moved to the next slide. Is it moving?
Yes,
Yes, sir, it is.
Okay. Okay. So now what will be the rate of heat input to the shell at the position R? That is going to be the area into the flux. So area is 2 pi RL into QR at the location R, isn't it? Similarly, the heat output from the shell is going to be 2 pi RL QR at R plus DR, isn't it? Because the radius outside the shell is going to be R plus delta R, isn't it? Thickness of the shell is delta R. Similarly, the rate of heat generation in the shell is going to be volume into volumetric rate of heat generation, isn't it? So volume here is going to be what? 2 pi R delta R, that is the volume of the shell, into L, isn't it? And multiplied by volumetric rate of heat generation, which is nothing but psi V. So rate of heat generation in the shell is going to be 2 pi R delta R L psi V. Okay. The heat balance in this case is going to be what? Since the accumulation we are assuming to be 0, rate of heat input plus generation should be equals to output, isn't it? Input plus generation should be equals to output. So we can put this input, output and generation term in this equation, and what we get is this equation. We can rearrange this equation. So what we get is RQR at R plus delta R minus RQR at R divided by delta R plus R psi V equals to 0, isn't it? This is just by rearranging this heat balance equation. So here you can see there is a common 2 pi L is a common, so that we can take out from this entire equation, and this delta R is there in the generation term, so that is divided to this entire equation. So what we get is the final equation in a differential form. Okay, so in a differential equation form, when delta R tends to 0, remember the shell is of infinitesimally small thickness, so delta R definitely tends to 0. For this particular condition, this difference equation which we had can be represented as a differential equation. So what we get is minus d by dr RQR plus R psi V equals to 0. That is equation number 1. Isn't it? So equation number 1 we can obtain by making a heat balance across the shell, across the element, and based on that the equation 1 is obtained. Now in this equation number 1 there is a QR term is there, which is nothing but the flux at the radius R, isn't it? So heat flux at the radius R can be again we can write based on the Fourier's law of heat conduction. So QR can be written as minus Km dTm by dr, that is given by equation number 2. Isn't it? So QR is written as minus Km dTm by dr. So we can put this heat flux in equation number 1. If you put this heat flux in equation number 1, what we get is this minus sign will get cancelled out with this, and Km being a constant value, it is not varying along with the temperature. So we can take this out from this differential equation, and based on that what we get is equation number 3. So equation number 3 is d by dr R dTm by dr plus R by Km psi V equals to 0. So this is the equation. Okay. So equation number 3 is the equation which we have obtained after making a heat balance and then putting a Fourier's law of heat conduction, isn't it? So what are the boundary conditions? The boundary conditions are very important. Just pay attention here. So the boundary conditions here is at R equals to 0. R equals to 0 means it is the center of the wire, isn't it? At R equals to 0, dTm by dr equals to 0. What it means is we are assuming that the temperature Tm is going to be a finite value at the center, and therefore this boundary condition dTm and dr equals to 0 is there. Okay, so at center the temperature Tm is finite, and therefore dTm by dr is going to be 0. Okay. The next boundary condition is at R equals to Ri. At R equals to Ri means this is the boundary of the metal wall. Remember, I can go back and show you. Remember here, there is a metal up to Ri, and above Ri to R0, there is a insulation. So insulation material is a different material, isn't it? So metal is up to only Ri. Okay. So the second boundary condition here is R equals to Ri, which is nothing but the boundary of the metal wall. The temperature Tm is going to be Tc. Remember, I said that the temperature inside this insulation is denoted by Tc, isn't it? So the temperature exactly at the boundary of the metal wall and the insulation is going to be Tc. Okay. Now, the important thing here is the first boundary condition. If you look at the first boundary condition at R equals to 0, dTm by dr equals to 0, applying this first boundary condition is easy. You can easily apply. But second boundary condition R equals to Ri, Tm is equals to Tc. This second boundary condition is difficult to apply. Why it is difficult to apply? Because we don't know what is the temperature Tc at the boundary of the metal wall. We only know the temperature outside the insulation. We don't know at the boundary of metal wall and the insulation, isn't it? So this Tc at the boundary of metal wall and the insulation, that we don't know. So applying the second boundary condition is not easy. For applying the second boundary condition, we need to solve the heat balance also in the insulation. Not only, see, up to equation 3, we have solved the heat balance only in the metal wall, isn't it? But since the second boundary condition requires the temperature outside this metal wall and at the boundary of the metal wall and the insulation, we also need to solve the heat balance in the insulation layer. So we need to solve the heat balance also in this insulation layer, which is outside this metal wall here. Is it clear to everyone? Are you all able to follow what I'm saying?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So let us first solve the heat balance in a insulation layer. Okay, insulation layer again. See, the heat balance for the insulation layer is also going to be the same as equation number 3, but the only difference in that case is going to be, remember, there is no heat generation in the insulation layer. There is no current flowing in the insulation layer, isn't it? Current is only flowing through the metal wall, and therefore heat generation is taking place only in the metal wall. So you can see in equation number 3, there is a R by Km psi V is there. So this is the term which is coming from the generation, isn't it? So this generation term is going to be absent if we are looking at the heat balance in the insulation layer. So for insulation layer, what we are going to get is the expression what we are going to get for the insulation layer using the heat balance. I am directly writing it, but you can also get the same term by making a shell balance in the insulation layer. So that comes out to be d by dr r dTc by dr equals to 0. So equation number 4 is the equation what we are going to get for heat balance in the insulation layer. So there is no generation term. There is no generation term here. Okay. Is it clear?
Yes, sir.
So now let's make the boundary condition for this. The boundary conditions are going to be what? Again, at R equals to Ri. So that is the boundary of the metal wall and the insulation layer. So Tc is same as Tc. And at R equals to R0, the Tc is T0. Outside temperature is T0, isn't it? So these are the boundary conditions. Again, here the first boundary condition is difficult to apply because Tc we don't know. Tc we don't know at the metal boundary and the insulation layer we don't know. We only know the temperature outside. Okay. So now in order to solve, see this unknown, in order to get rid of this unknown variable Tc, we have to solve both these temperature distribution in the metal wall as well as the temperature distribution in the insulation layer together, and then we have to apply the continuity equation. That is what we are going to do. Okay. Okay. So let us go back now, since the picture is clear to all of you. Let us go back to our metal wall again. So let us go back to this, uh, the metal wire. So metal wire temperature distribution in the metal wire is given by equation number 3. So equation number 3 again I have written here. So equation number 3 is integrated. So by integrating equation number 3, what we get is R dTm by dr equals to minus R square by 2 km psi v plus C1. Just check whether you all are getting the same expression.
Yes, sir.
So now let us apply a first boundary condition. I said that, you remember the first boundary condition, that is dTm by dr equals to 0 at R equals to 0. This boundary condition we can directly apply here. So this left hand side of this equation becomes 0. Again, R is 0 at the center. So C1 becomes 0. So what we get is R dTm by dr is equals to minus R square divided by 2 km psi v. Isn't it? So that means the constant C1 is 0. So from equation number 3, what we get is R dTm by dr equals to minus R square by 2 km into psi v as shown in equation number 6.
So could you please repeat once again why we had dTm by dr is equal to 0 for R equal to 0?
Because we are assuming that at the center Tm is going to be finite. At the center Tm is going to be finite. That is what is the assumption. In fact, this particular boundary condition is so commonly used. If you all have done your transport phenomena, have you all done your transport phenomena?
Yes, sir.
Yes, sir.
So this boundary condition is regularly used when you are looking at the condition at the center. Okay. Okay. So the expression which we have obtained is the equation number 6, which is R dTm by dr equals to minus R square divided by 2 km psi v. Again, we can integrate it one more time. So by integrating one more time, what we get is Tm equals to minus R square by 4 km into psi v plus C2, where C2 is the another constant. Okay. So again here C2 is unknown. C2 is unknown. And I cannot apply the second boundary condition. As I already said, this second boundary condition I cannot apply because I don't know what is the value of Tc, isn't it? Correct. So equation number 6 is the expression we have obtained. Now before we solve this equation number 6, because C2 we cannot get because we don't know what is the value of Tm, even though the second boundary condition is saying Tm equals to Tc. But in order to get a better picture, let us go back and solve the heat balance for the insulation layer first. So then we will have some more clarity here. Okay. So heat balance for the insulation layer is this: d by dr equals to d by dr into R dTc by dr equals to 0. That is what we have obtained. Remember here, this is the equation number 4. D by dr in the bracket R dTc by dr equals to 0, isn't it? So let us start with this equation. We can integrate this equation twice. So by integrating this equation number 4 twice, what we get is Tc equals to C3 ln R plus C4, isn't it? Now in this particular equation, C3 and C4 are the another integration constants. Again, we cannot apply a first boundary condition here because the Tc at the boundary of metal wall and the insulation we don't know, even though the boundary conditions we have written in both the cases. Here also we have written at R equals to Ri, Tm equals to Tc. Here also we have written at R equals to Ri, Tc is Tc. But both these boundary conditions cannot be applied because you don't know what is the value of Tc. Okay. So now let us simplify this expression of Tc which we have obtained. So we can just put the boundary conditions here. So Tc becomes C3 ln Ri plus C4, and the second boundary condition becomes T naught equals to C3 ln R naught plus C4. That is what is being given, isn't it? The first boundary condition is at R equals to Ri, Tc equals to Tc, and R equals to R naught. Tc is Tc Tc is equals to T naught. So that is what we have put here. So both these expressions are obtained. Okay, we can subtract this. By subtracting this, what we get is Tc minus T naught. So we have got rid of this C4. So Tc, remember our unknown is C3. So we will keep this unknown C3 till the end, unless we have matching with respect to the temperature distribution of the metal wall and the insulation. Till that point we will keep this C3 as unknown. So by subtracting these two equations, Tc minus T naught is going to be C3 ln Ri minus Ri by R naught. So by rearranging, what we get is Tc equals to T naught C3 ln Ri R naught. So in this equation both are unknown. Tc is unknown as well as C3 is also unknown. Okay, so this is equation number 7. Now from equation number 6, what we have obtained is Tm equals to minus R square by 4 Km psi V plus C2. Remember, again the second boundary condition was what? Second boundary condition for this metal wall was what? R equals to Ri, Tm equals to Tc. Correct. So this R equals to Ri. If this R equals to Ri, this Tm equals to Tc. So we can write this here. R equals to Ri, Tm equals to Tc. So this becomes Tc Ri square 4 Km psi V plus C2. And this Tc can be replaced by equation number 7. So this Tc which we have obtained here can be replaced by equation number 7. So we can put it here. So that becomes T naught plus C3 ln Ri by R naught. And that is equals to minus Ri square, because remember this is going to be at Ri, isn't it? This we want at Ri, isn't it? This is at Ri. So this becomes Ri square divided by 4 Km psi V plus C2, and that is equation number 8. The point to note down here is, remember, for deriving this equation number 8, we have derived this equation number 8 in this specific form where C3 and C2 both constants are there, because what we have argued earlier is because the second boundary condition cannot be applied directly, and in the second case also this first boundary condition cannot be applied directly. That means the constant C2 here and the constant C3 here cannot be obtained directly. We have obtained the final temperature distribution in terms of both these constants. We have obtained the final temperature distribution in terms of both these constants. Okay, so that is what the equation number 8 is. So here C3 and C2 both are constant. Now the next question is how to find out C3 and C2. Okay, so we require one more equation. Remember, this is equation number 8. There are two constants C3 and C2. We require one more equation in order to obtain C3 and C2. So in that case, we will have two equations, two unknowns we can find out. Okay. Sorry. Okay. Let me go back to the geometry. So what is happening here at the boundary? At this boundary of the metal wall and the insulation, whatever the heat is, the rate of heat transfer is there from the metal wall to this boundary, the same heat will be taken out from the insulation at this boundary, isn't it? So there is a continuity of the heat taking place exactly at the boundary of the metal wall and the insulation. So we can use the continuity equation at this boundary in order to obtain both these constants. So if we use the continuity equation here, we will have two equations, two unknowns, and we can find out. So let us apply the continuity equation. So this is the final expression which we have obtained, equation number 8. There are two unknowns. The continuity equation at the interface is going to be what? The rate of heat flow should be same from the metal wall to the insulation, and that should be the same heat taken out from the metal wall to the insulation, isn't it? Correct? So we can write down this equation as minus Km dTm by dr. That is nothing but the heat is transferred from the metal wall to the insulation, isn't it? And that should be same as the heat taken in the insulation is minus Kc dTc by dr. And this has to be true only at R equals to Ri, where R equals to Ri is nothing but the boundary of metal wall and the insulation. Correct? So with this equation, now we can solve equation number 8 and this equation new equation, and we can find out C1, C2, C3 and C2. So let us obtain dTm by dr. So we have obtained the expression of dTm by dr earlier. So this is the equation of dTm by dr. If you look at this is the dTm by dr, isn't it? And this equation number 6 is the equation for dTm by dr. So this r square will get cancelled out. It becomes r by 2 km psi v. Again, this equation we want at r equals to ri. So this r becomes ri. Isn't it? So Tm is so dTm by dr is given as minus ri by 2 km psi v. This is from equation number 6. Again, we can multiply by km, so that becomes km dTm by dr, and that becomes ri divided by 2 psi v. This is directly from equation number 6. You can go back and see. This is the equation number 6. Here, this equation number 6 we wanted to obtain at r equals to ri, because this entire analysis of continuity we are doing it at the interface of metal wall and the insulation, and therefore r is equals to ri. So this becomes dTm by dr becomes minus r by 2 km psi v, and km dTm by dr becomes r by 2 psi v. Sorry, ri by 2 psi v. So that is what is written here, isn't it? Ri by 2 psi v. Similarly, the TC we have already written in terms of this is what the equation we have written, isn't it? So dTc by dr, again, if you differentiate, remember this TC is given as C3 ln r plus C4. This is what we have obtained, the generalized expression. Here you can see TC is nothing but C3 ln r plus C4. Isn't it? That is what we have obtained by solving the temperature distribution in the insulation. So we can differentiate this equation with respect to r. So what we get is dTc by dr. So that becomes C3 by ri. And this entire thing is multiplied by Kc. So that becomes Kc dTc by dr is equals to Kc C3 by ri. And these two factors should be equated as per the continuity equation. So if we equate this, by equating these two factors, so these two factors are minus ri by 2 psi v. This is nothing but km dTm by dr at r equals to ri, and this should be same as Kc C3 by ri. So that is nothing but Kc dTc by dr. So by doing that, we directly obtain C3. So C3 comes out to be minus ri square by 2 Kc psi v. So this is the constant now we have obtained. Now here you can see the C3 is not in terms of TC. The point to be noted here is C3 is not in terms of TC. C3 is now, if you look at equation number 9, C3 is in terms of Ri, which is known. C3 is in terms of psi v, which is known, and Kc is also known. So all the variables in equation number 9 are known. Okay, if we can put this equation number 9 in equation number 8 and we can calculate C2. So C2 is calculated as, by putting in equation number 8, the C2 is calculated as T naught plus Ri square psi v by 4 in the bracket 1 by Km minus 2 by Kc ln Ri by R naught. Just check whether this is correct or not. Just check whether the given equation is correct or not. Is it correct? The last equation for C2.
Yes, yes.
So are you all getting why we have, solved the temperature distribution in the metal wire first, and then we have solved in the insulation, and then we have applied the continuity equation, and then we have obtained all the constants, isn't it? Correct? Is it clear to everyone? Yes or no?
Yes, sir.
Okay. So once we have obtained C3 and C2, we can put C3 and C2 in equation number 8 and in equation number 6 and 7, sorry. And remember 6 and 7 are given. If I go back, 6 is giving me the temperature distribution, isn't it? This 6, this gives me a temperature distribution in the metal wire, and 7 gives me the temperature distribution in a insulation. So I can put C2 and C3 directly in these two equations, and I can get the temperature distribution in the metal wire, and I can get the temperature distribution in the insulation. So that is what is being done here. So once we have obtained C2 and C3, we can put it in 6 and 7. So Tm is obtained as, remember this is the expression which we had, minus R square by 4 Km psi V plus C2. I can put C2 directly here. So by putting C2, what we get is the expression is T naught plus psi V by 4 Km R1 square minus R square. Sorry, this is Ri. This is Ri. Okay, this R instead of R1, this is Ri. Okay, minus Ri square by psi V divided by 2 Kc ln Ri by R naught. Okay, let me just check whether I can change. Okay. And similarly, if I put C3, if I put C2 in TC expression, what I get is this. So TC is given as Ri square by 4 Km psi V plus C2, and this C2 is replaced by this. If I put this, ultimately what we get is T naught minus Ri square psi V divided by 2 Kc ln Ri by R naught. Okay. Again, here one thing to note down is this temperature distribution in the insulation is valid only for Ri greater than sorry, R is greater than Ri. This is valid only for R is greater than Ri. Okay. So this is exactly at the boundary. This temperature is exactly at the boundary, but we can find out the distribution if this is not exactly at the boundary. We can have the distribution in between Ri to R naught also. Okay. This is exactly at the boundary. This TC is calculated exactly at the boundary R equals to Ri. But if R is not equals to Ri, still you can calculate, and that you can directly obtain by putting, I can go back, that you can directly obtain by putting, remember here we have put the C2, but if you put C3 and C4 in this particular equation, then you will get the distribution for TC. Now this equation is exactly at the boundary. I can write down also that instead of, so this is exactly at the boundary of metal and the insulation. Just give me a minute time. Let me just. Okay, done. Okay, this is exactly at the boundary. But if you wanted to know the temperature exact temperature distribution, for temperature distribution, one need to solve equation number. So let me just write down that also. For temperature distribution, put C3 and C4 in equation in equation number 7. Okay. Okay, so if you do not have any questions, we can move to the next case of the heat generation in the spherical geometry. Okay, so let me just go to the next. Okay. Now similar to the cylindrical case. Now cylindrical case was slightly more complicated because we have assumed that there is a insulation outside the outside the cylinder. Of course, this entire analysis can be simplified also. If you don't assume that there is no if you assume that there is no insulation outside the uh, cylindrical wire, then this entire analysis further simplifies, because then you don't need to solve the temperature distribution outside the metal wall. Okay. Now let's look at the spherical case. So in this particular case, we are not assuming any insulation outside the spherical boundary. Okay. So again, similar to the previous case, since the heat transfer area is the area which is present at the radial positions, and that is vary as I am moving from center to the outside radius. So clearly the area of heat transfer is varying. Also, there is a heat generation is taking place inside the spherical uh, the spherical system here. We need to make a shell balance, and again the rate of heat input to the shell at the radial position we can just write as the surface area into the heat flux. So that becomes 4 pi r square QR at R. Similarly, the rate of heat coming out from the shell at the radial position R plus delta R is going to be again 4 pi r square QR at R plus delta R. The rate of heat generation in the shell is going to be volume into volumetric rate of heat generation. So that becomes 4 pi r square delta R psi V. And at steady state, we are assuming no accumulation here. So input plus generation equals to output. So we can put all these terms in this equation. So what we get by rearranging this equation is minus R square QR R plus delta R minus R square QR at R divided by delta R plus R square psi V equals to 0. So we are assuming that the volumetric rate of heat generation psi V is uniform throughout the sphere and is not varying with the radial position. Okay, so it is constant throughout, and also thermal conductivity we are assuming constant here. So this difference equation which we have obtained here can be written in terms of differential equation, because this shell which we have considered here is of the infinitesimally small thickness delta R. So we can write down this difference equation in terms of a differential equation as minus d by dr R square QR plus R square psi V equals to 0. So this is equation number 1. So now if you look at your heat balance for the slab, in the slab the heat balance you have obtained is minus d by dx qx plus psi V equals to 0. For the cylindrical case, you have obtained the heat balance as minus d by dr rqr plus r psi V equals to 0. And for the case of sphere, you have obtained as minus d by dr r square qr plus r square psi V equals to 0. So there is a some common features between these three equations, if you notice clearly. Okay. So as we are moving from planar to cylindrical and cylindrical to the spherical, the term R is added here. Okay. Again, in this equation number 1, we can put the Fourier's law of heat conduction. So QR is written as minus k dt by dx. If you put it here, what we get is d by dr r square k dt by dr. plus r square psi v. There is a additional plus is there. So this only one plus is here. So d by dr r square k dt by dr plus r square psi v equals to 0. So that is the equation. So now we can integrate, we can rearrange this equation. So r square psi v we can take it on the right hand side, and k is constant, so that we can take out from this differential equation. So that becomes the right hand side becomes minus r square psi v by k. Again, if we integrate with respect to r, what we get is r square dt by dr equals to minus r cube psi v divided by 3k plus c1. Again, the boundary conditions are same here. The boundary condition here is r equals to 0 at r equals to 0. The temperature at the center is finite, and therefore dt by dr equals to 0. This is the first boundary condition. And the second boundary condition is at r equals to r naught, t is t naught. So clearly here you can see the second boundary condition is easy to apply, unlike the previous case. In the previous case, outside the metal there was a insulation, isn't it? So unlike that, in this case there is no insulation, and this outlet temperature we already know, this T naught is known to us. So we can directly apply the second boundary condition, unlike the previous case. So both these boundary conditions we can apply easily. So let us apply the first boundary condition in equation number 2. So by applying the first boundary condition, this dt by dr becomes 0. So here by applying the first boundary condition, you can clearly see you will get C1 is equals to 0, and based on that, if I put it this C1 equals to 0 in equation number 2, what I get is r square dt by dr equals to minus r cube psi v by 3k. And again, if we rearrange the term, dt by dr becomes minus r psi v by 3k. And if we rearrange again, if we integrate this particular equation, what we get is t is obtained as minus r square psi v by 6k plus c2. So whether the slides are visible to everyone? Hello?
Yes, sir, they are.
Okay, so this is a simpler case compared to what we have seen earlier. So what we get is the temperature T can be obtained as minus r square psi v by 6k plus c2. Again, if we apply the second boundary condition here at r equals to r naught, t equals to t naught, so we get t naught equals to minus r naught square psi v divided by 6k plus c2. So by rearranging this, c2 is obtained as T naught plus R naught square psi v by 6k, and after rearranging, the temperature distribution can be obtained as T is given as T naught plus psi v divided by 6k in the bracket R naught square minus R square. So equation number 3 is the temperature distribution equation for the case of the spherical system in which there is a heat generation is taking place internally. So this temperature profile is parabolic in nature, and again the question could be what will be the maximum temperature. So maximum temperature and where it will be. The maximum temperature definitely will occur at the center, isn't it? So if you look at equation number 3, the T is decreasing as the value of R is increasing, isn't it? Correct. So the maximum temperature can only be possible at the center when R equals to 0. So clearly the T max you can obtain directly by putting R equals to 0. So that comes out to be T max is given as T naught plus psi v R naught square by 6k. This is the maximum temperature. In a similar manner, I have not derived, but this cylindrical case, remember this cylindrical case, if we don't assume that there is a insulation, you can do the similar analysis as we have done for the spherical case, and we can obtain the maximum temperature. You can see the maximum temperature will occur at the center, isn't it? So without the insulation, solving this particular cylindrical case becomes easy, because then this is the expression 3. Here this at R equals to Ri, Tm equals to Tc is given. So instead of that, we will have Tm equals to T naught. And the solution becomes very easy because we don't need to solve this heat balance in the insulation. We can directly solve the heat balance only in the metal wall, and we can apply both these boundary conditions, because in that case this T naught is going to be known. Here remember, this Tc is unknown. But if we are assuming there is no insulation outside the metal wall, then this Tm becomes T naught, and then we can we can just apply this first boundary condition is directly applied here. We can integrate this here, and here we can, in equation number 6, we can apply the second boundary condition directly. So Tm will be T naught, and that will become minus R square by 4 Km psi V. T naught equals to R naught square divided by 4 Km psi V plus C2. So we can directly obtain C2, and if we rearrange this, what we will get, the expression for Tm, throughout the metal wall. Okay, clear? So we have solved the complicated case in the cylindrical system, but you can solve the simpler case when there is no insulation outside. Okay, is it clear to everyone? Is it clear to everyone?
Yes, sir, it's clear.
Okay. So now let us solve one example based on this. Let us solve one example based on this. Okay. So this example is visible to everyone?
Yes, sir.
Okay. So now in this particular example, what is been given is a current of 200 ampere is passed through a stainless steel wire. The thermal conductivity of the metal wire is given, that is 19 watt per meter degree Celsius. And again, it is a 3 mm in diameter. This metal wall is a 3 mm in diameter. The resistivity of the steel may be taken as 70 micro ohm centimeter, and the length of the wire is 1 meter. This metal wire is submerged in a liquid at 110 degrees Celsius and experiences a convection heat transfer coefficient of 4 kilowatt per meter square degree Celsius. Calculate the center temperature of the wire. So here the convection we are referring to, but convection for a time being, do not worry about this term. Anyway, we have seen the Newton's law of cooling, isn't it? So that is, this convection heat transfer is the proportionality constant there. So that is the only thing I am telling you now. We will look at this heat transfer coefficient and the convective heat transfer in much more detail later. But for a time being, you can just assume a Newton's law of cooling, and anyway, based on that we can solve this. Okay. So what we are looking at, we wanted to find out the center temperature of the wire. Center temperature of the wire we wanted to find out. That means the temperature, maximum temperature which is present at the center of the wire we wanted to calculate. Remember, this is the same case as that of the cylindrical wire which we have seen earlier. But the difference here is there is no insulation outside. Now there is no insulation outside the metal wire. There is a directly the the liquid temperature will be there outside the metal wire, that is 110 degrees Celsius. We don't need to solve the temperature distribution in the insulation what we have seen in the cylindrical case earlier today. Okay, so let us solve this problem. Okay, so what is been given is the current of 200 ampere is flowing. Now definitely there is a resistance in the wire, and because of this resistance the heat will be generated inside the wire, and this heat is dissipated to the liquid which is outside the wire. That is what the system is. Correct. So first calculate how much heat is going to get generated because of flowing of the current. Now the heat generated Q will be same as the power, that is given as I square R. The square of current into the resistance, that will give you the Q, and this Q is going to be the same as the heat dissipated to the liquid, and heat dissipated to the liquid is given by the Newton's law of cooling. So Newton's law of cooling gives me the heat dissipated is proportional to the temperature difference. So this is the temperature difference, TW minus T infinity. So TW is nothing but the temperature of the wall, and T infinity is nothing but the temperature of the liquid. Temperature of the liquid is given as 110, isn't it? TW we have to calculate. Temperature of the wall we have to calculate. Okay. This is what, sorry. Temperature of the wall we have to calculate from the heat balance. Yes. Okay. Now what is been given here? What has been given here is the resistivity of the steel is given. The resistivity of the steel is 70 is given, but resistance is not given. Resistance we have to calculate. Based on this resistivity, the resistance can be calculated as rho into L by AC, where AC is nothing but the cross-sectional area of the wire. Cross-sectional area of the wire. Now what is the diameter of the wire? 3 mm is given. So what will be the cross-sectional area of the wire? Pi r square. So r in this case is going to be 15 mm. So that is going to be pi into 0.15 square. Into rho is already, the resistivity is already given, that is nothing but 70 micrometer. So micrometer is given. So that is why we have multiplied by 10 raised to the power minus 6. Again it is multiplied by centimeter. So this L has to be there. So this L has to be in the centimeter. So 1 meter is there. So that is written in terms of this centimeters. That becomes 100. Okay. So this becomes, just wait. I think some confusion is there. Correct. So by putting all the values, the resistance obtained is 0.099 ohm. And this resistance we can put it in this the equation of Q. So by putting this resistance in this equation of Q, I square R is calculated as 200 square into just wait. I think I messed it up somewhere. Calculate the value of R. Just calculate the value of R. Did I made some mistake here? Okay, I think now it is correct. So this becomes 200 square into 0.099, and that becomes Q, and the Q is equals to HA into delta T. Here H is nothing but the heat transfer coefficient, which is already given 4 kilowatt. So that becomes 4 into 1000, 4000 into area. Now area is what? Area is what? The radial surface area of the wire. That is going to be pi dl. Isn't it? So that becomes pi into diameter, which is nothing but 3 into 10 raised to power minus 3. Length of the wire is 1 meter. So that this becomes pi dl into delta T, TW minus T infinity. So T infinity is already given. So the temperature of the bulk of the liquid is given 110. So 110 is there. TW minus 110. So only unknown in this case is TW. So TW we can calculate as 215 degrees Celsius. So TW comes out to be 215 degrees Celsius. Again we wanted to calculate what will be the volumetric rate of heat generation. So remember this Q we have already calculated, which is 3960. Remember here nothing, the heat is not coming in, the heat is only generated. So whatever is the Q, that is all the heat generated. That all the heat generated, this Q divided by the volume of the wire will directly give me the volumetric rate of heat generation. Isn't it? So this Q is given as psi V into V. I can directly obtained psi V. So psi V comes out to be 3960 divided by volume of the wire. So that becomes pi r square into L. So if I put all the values here, psi V comes out to be 5.602 into 10 raised to the power 8 watt per meter cube. Now we can calculate the temperature at the center. The temperature at the center can be obtained as Tm can be obtained as psi V r square 4k plus Tw. This can be directly obtained by solving this equation. You can solve this equation. You can solve this equation. So if you rearrange this equation at the center, so at the center what you get is, so again in this equation C2 you can obtain by putting the another boundary condition. So that is another boundary condition is at Tm equals to T naught at R equals to R naught, and then you find out the temperature at the center. So if you find out the temperature temperature at the center, that comes out to be this temperature which I have directly written here. Tm equals to psi V R square 4k plus Tw. So this will be R naught. So in this case that subscript is omitted. So that becomes psi V R square by 4k plus Tw. This is the final expression which you are going to obtain by solving the same cylindrical equation which we have seen earlier. I have directly written that equation, but I request all of you to solve that equation for the center temperature and then see whether you all are getting the same equation or not. So by putting all the values in this equation, ultimately the wall temperature, the temperature at the center is obtained as 231.6 degrees Celsius. So the temperature obtained is 231.6 degrees Celsius. Are you all able to follow? Hello?
Yes, sir. Sir, can we use the standard results directly which you have derived in class?
Yes, you can use that also. Yes, you can use that also. You are saying, let me just go back.
Like substituting C2 directly and the final equation using it directly.
This equation you are saying?
Yes, sir.
This equation you are
use this one only.
Yes, this equation also you can use. This equation also you can use. If you put Ri equals to 0, this entire thing becomes 0. This again Ri, this becomes 0. So what you are going to get is T naught at the center. You are going to get what?
Sir, Ri will be equal to R naught actually.
Ri is going to be
R naught because we don't have insulation now. So there will not be any R naught minus Ri.
Correct. So Ri minus R naught will not be there, you are saying. So
yeah, Ri will be R naught actually simply.
Yes, sir.
So in that case, Ln term will be cancelled out.
Yes, this will get cancelled out. How
but
about
on the left side
term?
as well? This was Ri, no?
This will be Ri square minus R naught. Ri square minus R. So this will becomes
Ri square only because R is 0.
Correct. But I am looking at whether this minus sign. Just check whether this minus sign is here or not. Just check with this equation. Okay. Can you check this equation?
So it is coming though, it's from the above equation, it's following directly.
Okay.
It's a positive sign that's coming in.
No, positive sign is coming in, but this equation is correct or not. That is what I'm trying to see. Whether this equation is correct. This equation is correct. Is it correct, this equation?
Yes, sir, both are the same. Both of them had the positive sign.
Okay. Just check whether you are getting this equation from this or not. Okay.
Okay, sir.
Okay, so this equation is correct. This you can derive also. This you can directly derive instead of instead of rearranging the final expression. You can derive directly from the cylinder, the equation of the cylinder just by uh, you know uh, just by having the metal wall without the insulation. So that case you can yourself derive. Okay, so can we move to the next topic? Hello.
Yes, sir. Yes, sir.
Yes, sir.
So I will just give a brief overview of the next topic, and then we will not do anything new in this, and then we will stop. Okay. So far what we have seen, we started with a very simple case when there was no variable area. Then we moved to a slightly more complicated case when there was a variable area. Then again we have moved to another complication where we have assumed that there is a generation term is there, isn't it? And extending that to further, now we are assuming that there is a accumulation term is also there. Okay, so what is going to happen? We started with a very simple case with nothing was there, very simple plain geometry with no variable area, no accumulation, no generation. We slowly added the variable area, then we slowly added a generation term, and now we wanted to add the accumulation. So whenever we add the accumulation term in the heat balance or the mass balance, what we get is a unsteady state, isn't it? Because accumulation term will have dou by d by dt or dou by dt dou by dou t term, isn't it? So that will give me how my temperature is going to vary with respect to time also. Correct. So in the next class, what we are going to look at the unsteady state conduction in a rectangular solid. Again, we are start with a very simple case of rectangular solid. Then we will move to cylindrical geometry and then spherical geometry, isn't it? So here, if you look at uh, the uh, the uh, the flat slab is there. A flat slab is there. Again, in this particular flat slab, there is a generation of the heat is also taking place. Then there is a accumulation of the heat is also taking place. So for this particular flat slab, definitely we need to make a shell balance, isn't it? So consider a small shell which is shown inside here. So this small cube which is there inside this outer cube, this is nothing but the elementary small element of volume delta x, delta y, and delta z is assumed. This element is then shown in on the right hand side is enlarged here on the right hand side. So here you can see the sides of these the rectangle is delta x, delta z, and delta y along the individual axis x, z, and y. Again, if you look at the point A, the point A is basically 0, 0, 0, isn't it? So the x-axis, the axis x, y, and z axis are already shown here. You can clearly see. So there is a heat input taking place. The heat input taking place from the surfaces uh, ABGF, ABEF, and ABEF, ABGF, and there is a last surface is also there. Let me just correct it. The last surface is ABCD. So let me just correct that. Okay.
Answer ADEF.
Only from the three sides it is
Yes,
coming.
yes, sir. It'll be AB instead of ABEF. I guess it should be ADEF. No, ABEF is not a surface.
Let me just check. ABEF is not a surface. You are right. That should be ADEF.
ADEF.
Correct.
ADEF.
Correct. Thank you. Okay. Okay. some small mistakes would be there because all these slides are newly prepared this year. So I just have to translate it from my class notes to the slides. So some mistakes are occurring there. So please correct me in between if I am not correct somewhere. Okay. Okay. So there is a heat input from these three surfaces, and then there is opposite surfaces of these. There will be a heat output, and then there is a rate of heat generation term is there, which is nothing but delta X, delta Y, delta Z. That is nothing but the volume of this element, the small element here, and multiplied by volumetric rate of heat generation. And then there is a accumulation term which is dou by dou T, volume multiplied by rho Cp dt, isn't it? So this is going to be the rate of heat accumulation in the system. So we can make the heat balance of this entire thing. And then the heat balance is also we have made here. But anyway, we will continue with this in the next class. Okay. So we stop here unless you have any doubt, any question to ask.
Hello, sir.
Please go ahead.
So it's been a week since we've taken this course, and sir, we have realized we most definitely require the class slides.
I will supply the class slides, no problem.
All right, sir. Thank you.
I will give the class slides, but see, the only reservation I had for not supplying the class slides was then you will not go through the books. Many of you, many of your friends, and they will look at the slides on the last day of the examination, and based on that they will write their exams. So that I definitely don't want. I want students to go through the book because see, there is a limited material which I can use in the class or in the slides. I cannot put everything whatever is there in the book, but in the book you can find several more problems are solved. Also some more small concepts are there which I generally talk about. It becomes difficult for me to write it on the slides. So you get familiar with those if you go through the book. Okay, but doesn't matter. I will definitely provide the slides. If you guys insist, there is no problem. Okay.
Sir, can you please
Yes, sir.
provide
Thank
the
you so
slides
much.
after the lecture, after every lecture?
Uh, Once we complete a particular topic, that entire slide I will upload.
So the thing is
For example, once the conduction part is completed and I move to convection, then entire conduction slide I will upload.
Yes, sir, but the thing is that we have to take notes, and taking notes in class is not possible because of the speed. So we require the slides to make notes, and otherwise we are not prepared for the next class. So as you saw today also, we were not really prepared for what we were doing today, because like many of us haven't been able to complete the previous slide notes.
Class videos are already available, isn't it? Why I am don't wanted to submit, because I am keeping this PowerPoint open, because once I switch off, then it becomes difficult for me to change the equations. You can clearly see the earlier slides. I am not able to change the equations. See here, I cannot change the equations. Once I close this window, all these equations kind of become fixed. Uh, if I have to change a slide thing here, this entire slide I have to write one more time. So that is the limitation. That is why I am not closing this window unless this entire topic is done. So can you bear with me for a time being? Maybe just one more class will be required to complete the unsteady state, and then probably okay, or otherwise I will make the unsteady state slides, separate slides for the unsteady state heat conduction. Okay.
No, sir, it's fine. Like you please keep your own continuum so that your flow doesn't get disturbed. We'll manage accordingly.
No, sir. The thing is that you can divide the slides, like you can break them apart and then still be able to provide them, and you can keep saving your progress also as and when you change some equations or make an improvement.
I will put it as a save as, and then I will try to upload. I
Yes,
understood what you are trying to
please.
say. Yes. Okay.
Right, sir. Thank
Perfect.
you so much, sir.
But generally I will put it, see, instead of uploading every class, I will try to put it after completion of sufficient amount. Okay, so for example, now almost steady state heat conduction is done, so I will upload this steady state heat conduction part completely. Once the unsteady state is done, this entire conduction slide I will put it, and replace all other slides. Okay, clear?
All right, sir.
So
Sir,
any more doubt, any question? Yes, please go
yes,
ahead.
sir. Sir, can you specify the pages which we should have read about or book?
Book, I think conduction, let me just check how much we have completed so
Sir,
far. So if you ask me, more or less that entire book we are going to cover.
sir, there are
Complete book.
many pages, like 500.
I know, but this entire book we will cover in this course.
Sir, you can specify the pages like in previous subject CLL we have done.
No, see, the point is, I think how many chapters we have completed, that I can specify. Specifying the pages, because see, sometimes I am doing some small material from one page, some other material from some other page, isn't it? So it's like that, isn't it? So more or less I am going through the entire book. If you look at this, all this content in the slides, you will see that it is there in the entire chapter. It's not that I am, I am not, eliminating any material from the book. In fact, the entire book will be covered. There is some more amount of material added in the slide other than whatever is there in the book. But nothing which is there in the book is not eliminated at all. Nothing is eliminated from the book. Everything, whatever is there in the book, that I have more or less covered, more or less I'm going to cover in this course.
Yes, sir, we'll go through the book since last time we had transport phenomena, so it was the same there. We used to go through the book as well because we know both things are important.
Okay, any more question, any doubt, anything? Can we stop here?
Yes, sir.